in learning about conditional probability. That's why you're here. I know that's why you're here. So let's get right into it, and don't forget to check those extra examples in your book to help you out to learn a little bit better. Okay, so first of all, what is conditional probability? Let's define that, and then from there we can do some examples to flesh out the problems or flesh out the definition a little better. So the probability of an event, we're going to call this event E2, so E sub 2, a little 2, subscript right there, occurring given, put a comma there, given event E1. Very, very critical that you are given event E1. This has to happen first, basically. So given event E1 is happening, what is the probability of event 2 happening? This is called conditional probability. And it's written and is written like this. So if you're writing this, the shorthand notation for something like that looks like this. You have the probability of, and then event 2 happening given event E1. So if you're reading this out loud, let's get out a different color to describe what this would be read out loud. So if you're reading this, you would read this as probability of event 2, or of E2, you could call it that as well, of E2 given E1. So this straight line, it's kind of like a 1 but longer. It's like one absolute value symbol. It's basically the same symbol, but you don't have absolute value around the whole thing. It's just one long line. So this is read the probability of E2 given E1. So E1 has to happen. What's the chance that E2 happens given that E1 has to happen? That's another way to think of that. So let's check out an example, and we will deal with conditional probability here. So here's example 1. A single card is selected from a standard deck of cards. So I've got my standard deck down here again. Standard deck of cards. Find the probability it is a picture card given that it is black. So here is how we'll solve this one. A way we can write this is probability P of picture card. Then I can say given, not exactly sure why I wrote a G there, given black. So that symbol right there means given in terms of probability in the context of this problem. So what is the chance of this happening? So given black, if that has to happen, how many things do we have to choose from? How many black cards are there, in other words? If you count them up, it's going to be these 13, the clubs, plus these 13 spades. That's a total of 22 cards to choose from. So given black, we have 26. I said 22, I meant 26. I think I just said 22, but 26 cards to choose from. And so what do we have of those that are picture cards? Of those black cards, we're not even considering the red cards because we're given that we have black cards to choose from. So given black cards, we have 6 of those that are picture cards. So this becomes, out of the 26, you have 6. And so let's write down where these are coming from later on. When you look at this, it'll make a lot more sense if we know where they came from. So this was 6 black cards. I'm going to finish that thought in a second. Let's do this thought first, though. So there's only 26 black to choose from. There we go. So that's where the 26 comes from. It's not out of 52 because you are given black. Black has to happen. So 26 black cards to choose from, and 6 black cards are picture cards. So of the 6 black cards, you looked at those, you saw it down here. This is your sample space for all the cards. This is all the cards you can choose from. Only 6 of those are black and are picture cards at the same time. So that's why that number goes on top. This now is just a matter of simplifying one more step to get the final simplified answer would be 3 over 13. You can divide each part by 2, and that's what you get. Let's check out a second example. Here's what we got going on for this one. Assume a computer randomly generates a number, and that number is either going to be 1, 2, or 3. Randomly generates a number 1, 2, or 3 2 times in a row. And this one will have a couple parts to it. Actually 3 parts to it. Find the probability that, so we're going to go back a couple lessons here for this one. A 3 is generated both times. And so yes, it would be 1/3 times 1/3. That, going back one lesson, is all we need for that one. The multiplication formula for and probability problems, for that happening twice. You can think of it like that. I want to draw a tree diagram here, though, because this will help us see what our entire sample space is. We're going to see every possibility this way. So 1, 2, and 3, that would be what you would have for the first number. And then from there, if the computer generated a 1, it could still generate a 1. We're not saying that's gone. That's still an option. So it could be a 1, 2, or 3. If it generated a 2 first, it could randomly generate a 1, 2, or 3. And the same thing with a 3. So this would be your first number generated, the second number generated. So the sample space would include 9 different numbers. 3 times 3 is the number of ways that can happen. So we have a 1 and a 1, a 1 and a 2, and a 1 and a 3. You also have a 2 and a 1, a 2 and a 2, and a 2 and a 3, and a 3 and a 1, 3, 2, and 3, 3. And so what are the total number of ways? Let's put this in a different color. Right here there are 9 total sample points. Sample points. And so your probability is going to be that 3 generated both times. There's just one where that happens, is 3 and 3. So there's 1 out of 9 total sample points, 1 out of 9. So this is your final answer. For reference later on, let's, in a different color, let's put this off to the side here. Where did these numbers come from? This was the number of ways to get both as 3. So the number of ways to get both is 3. That was a 3 and a 3. 3, 3. And then this was the total number of possibilities. So going back still to what we want over the total, it's still totally based on that. What we want goes on the top, and what total number of ways it can happen goes on the bottom. So let's do a part B to this and throw a little twist into the situation. So part B for this question is going to be 2 2s are generated. This is part B. 2 2s are generated figuring out the probability of this happening. So 2 2s are generated if at least one of the numbers is a 2. When you see this word if in the context of a probability problem, you can essentially replace that with given that at least one of the two numbers, or at least one of the numbers is a 2. And so you could reread it, you could restate it like that. 2 2s are generated given that at least one of the numbers is a 2. So let's go back to our tree diagram, and you don't have to circle things here, but I'm going to look at my sample space and see where I have at least one of the numbers being a 2. So I have 1 here, then I have 2, 3, and 4 here, and then I have a 5th one there. So it looks like I have 5 different choices to pick from. This is saying given that this is the case. So given that I have at least 1 2, what's the probability that 2 2s are generated? So my total becomes 5. It's not 9 anymore. It's just the ones here that included 2. I have at least 1 2. And of those 5, only 1 is going to be having both 2s. It's going to have 2 2s. Let me erase that. I will refer back to that a little later again. But let's write that down. So the probability of both 2s, both being 2 in other words, given that at least 1 is a 2. So this was equal to 1 out of 5. We stated that already. Let's write it down though where these numbers came from again. And so this number, the number 1 up here, this was the number that are both 2s in the sample space. So that was the only one right there that were both 2s. It's number that are both 2s, and then we'll actually write down the sample points here. So that was the 2 2 one. And so this one was the number that have at least 1 2. And so that sample, or those sample points were 1 2 and 2 1, 2 2, 2 3, and then also 3 2. So those are the 5, and only one of those had both 2s. And then part C, let's do something with one more twist to it, still related, still connected to what we were doing back here. But let's say 2 2s are generated. So the same start as before in part B. 2 2s are generated if the first number is a 2. So again, think of it as a given. Sorry, I'm thinking of what I'm going to say next is a 2. So consider the word if again. You can reread this, rewrite this as 2 2s are generated given that the first number is a 2. So we could say this in the probability form, that both 2s, given that the first number is a 2. And so I hope at this point you're starting to see a pattern develop, that the number on the bottom is always this part. It's always the number of ways that this part, the second part, can happen. And so the given part, in other words, this is the given part. This has to happen. How many ways can you select, or how many ways are there where the first number is a 2? That would be this one, that would be this one, and that would be this one. Those are the only 3 now we have to pick from. So given that that first number has to be a 2. We only have 3 choices to choose from. So that goes on the bottom. So we'll put a 3 there. And how many are both 2s? Well, it's still just the 1. So the chance of that happening is less than before. So the conditional probabilities, when you hear somebody say, I'm going to do something on a certain condition or on one condition, that means it's dependent upon what you're saying or what that condition is. So assuming that this is true, I will do this. Assuming that this is given, what is the chance of this now? We're talking about that. That's what conditional probability is. So this number up here, it's the number that are both 2s. That didn't change from before. So the number that are both 2s, let's keep that in a different color here, the 2 and the 2. And then this number down here is going to be the number that have the first number. The number that have the first number as a 2. And that was, those sample points were 2, 1, 2, 2, and 2, 3. Okay, from there is a formula. I almost like to just think about it rather than try to memorize this formula, but I'm going to give you the formula. The formula is a conditional probability formula. That's what we'll call it. And we've been doing this already in this first example and the second example. We've been doing this and you didn't even realize it. We've been using this formula, but this is written out in a more precise form, I guess you could say. So the probability of event 2 happening given event 1 is going to be the number of things you have in common or happening in both of those things. And that's divided by the number of things happening in the given part, in the E1 part, the event 1 part. Another way to write this is using the set notation that we learned before. So given the number of things in their intersection divided by the number of things in the given part. So given that this has to be true. So this part down here, this is just the number of possibilities you have, the total number of things in the given part, and then this is the number of things that they both have in common. And so if you are using this specifically, you might be like, what's n stand for? I know that these are the 2 events, this is a probability, so let's just write that underneath here, where n represents the number of samples, the sample points, where n represents the number of sample points in the set in parentheses. So here the set in parentheses is E1 and E2, which you can write like that. Here the set in parentheses is just E1. So this is their intersection, this is just E1 by itself. Let's do a third example and we'll talk about this, and we'll talk about how you can just kind of think of it. You can intuitively come up with what goes on the bottom and what goes on the top based on just what you want over the total. Still thinking about that. It's still a probability problem, so that still definitely applies. So here's the problem for example 3, our final example. A survey of 100 teachers was conducted asking if he or she favored extending the school year. Now you may have some strong feelings about that, and I'm not going to tell you what I think. We're just going to look at the survey. So here are the results. So despite what you may think for or against extending the school year, this was the result of my fabricated survey here. So the the school is going to go here. Those in favor of, that's going to go here. Those opposed, that's going to go here. And the total is going to go there. So I'm going to say there was this school, Jefferson School, and the other school was Lincoln School. Often schools get named after famous presidents, so we'll say those are the two schools that got surveyed. There was 100 total teachers in all, and so that number is going to go here. But Jefferson, there were 33 in favor, and there happened to be 27 opposed, for a total of 60 teachers surveyed at Jefferson. And then at Lincoln, there were 15 teachers that were in favor and 25 opposed, for a total of 40. So the grand total is 100, like we should expect. The total in favor from both schools together is 48. The total opposed, 52. And here's the rest of the problem. If a teacher is selected at random, find the probability that the teacher, and then some different parts to this as well. So part A, favors an extended school year. What is the chance of a teacher favoring an extended school year based on the results of the survey? So this empirical data, this experimental data, based on the results of this, we're thinking of what we want goes on the top over the total on the bottom. So what do we want to happen? We want to know how many people favored it over the total. So there were 100 total people surveyed, and how many of those people favored that? That was 48. So 48 out of 100. You can reduce this. You could divide by 2, but then you could actually divide by 2 again. So you could just divide by 4 and get it all done at once. So this divided by 4 would be 12, and then 100 divided by 4 would be 25. That is not reducible any farther, so that would be a final answer. If you were to write this as a percent, anything divided by 100 is always per 100%, and so that would be 48% as well. We're going to write them as simplified fractions for right now, though. So let's say that this was true, this data was true. This is still going to hold true in parts, the other parts that we're doing here. I think we're doing 3 more parts here. So part B, now let's go back to that survey in just a moment, but right down here's part B. Favors an extended school year. So same start is what I just did for part A, but now given that. So this is now a conditional probability problem. Given that the teacher, we'll put a comma there, given that the teacher is from Jefferson. So now, this one I'm going to write out the slightly longer way. We're going to use the conditional probability formula. The other ones I'm going to condense a little bit more, show you what I think is an easier way to think about it. But this way I'll kind of share both with you. So the probability, I'm going to say favors given Jefferson. So we have to start with Jefferson. So given Jefferson is true, what's the chance that they're going to favor an extended school year? So let's in your different color. Under this, let's put E2. We're starting, or we're given Jefferson, so we're going to call that event 1. So given Jefferson, what's the chance that the second thing will happen, that they'll favor an extended school year? So this would equal, in terms of our conditional probability formula, we'll write it like this right now. So the number of events in E1, or the number of possibilities in E1 and E2 divided by the number of things in just E1. Another way to think of that is the number that favors, so that's what this N just stands for, it's a number that favors and is from Jefferson. That's my condensed way to write that. So number that favors and Jefferson, both those things happening, over the number in just Jefferson. That's what E1 is. E1 stands for just Jefferson. So what do we have? Let's go back to the survey results. How many were surveyed from Jefferson? Jefferson, total surveyed was 60. So our total in this case becomes 60. No longer 100, because we're given that we have to start with Jefferson. So we have 60 teachers to choose from given Jefferson. And how many of those were in favor of from Jefferson that were in favor of it? So Jefferson and favor right now. That's this number right here. So that's going to go right here, 33. And this you can reduce. You can divide by 3 and 3, it looks like. That would be 11. And this would be a 20. Can't reduce that anymore, so that would be the final answer there. So now part C. Let's change it up a little bit here again. So now opposes an extended school year. If the teacher, or if that teacher is from Lincoln. So I worded this a little bit differently because I just wanted you to see that it's going to end up being the same thing. So this is a continued sentence from this year. If a teacher is selected at random, find the probability that the teacher opposes an extended school year if that teacher is from Lincoln. So this, another way to say that, instead of if, you can say given that the teacher is from Lincoln. So what is this going to be? It's the probability that somebody opposes, and then given that they're from Lincoln School. So that's how we would set that one up. Could you write this and label these E2 and E1? Yeah. I think, though, this is what I was talking about earlier, where I'm going to try to condense things, just simplify them, make them easier to think about. So up here, we could just go to this idea. So what's the total things you have to choose from? Well, that's the total number of teachers from Lincoln that got surveyed. So given that, that's the part that goes on the bottom. The given that part goes on the bottom, and then what you want goes on the top. So let's put that in a different color. This is the given, or given that part. That's going to go on the bottom. That's what you have as your total things to choose from. And then this is still what you want on the top. So given that becomes your total now. So what you want over the total, still the same idea as before. And so what do we want to happen? We want to pick somebody that's opposing from Lincoln. So it has to be opposes, number that opposes, and is from Lincoln. So if we look at the survey results here, the total from Lincoln is 40, and the number that opposes and is from Lincoln is 25. So this would be a 25 out of 40. That you can reduce. You can divide both parts by 5. This would become 5, and this would become an 8. And so that would be the final answer there. So this is going to be true up here as well. This is still the want part, and this is the given that part, or the total part. Let's do one last part, and we will call it good for this lesson. So this one, probability that the teacher is from Lincoln. Given that the teacher opposes an extended school year. So now, if we look at this, this is basically this flipped around. So it opposes an extended school year if the teacher's from Lincoln. We switched these two parts around. So that the teacher is from Lincoln, given that they oppose an extended school year. And so now this becomes probability of Lincoln, given that. Notice I changed it back to given that instead of if that teacher, but it's the same thing. So probability of Lincoln, given that they oppose the extended school year. And so what's going to go on the top and what's going to go on the bottom? So on the bottom, it's going to be the given that part. This is what you have to choose from, the given part. And so the number that opposes now becomes the given part. So how many opposed this total? We had 52. How many of those that opposed were from Lincoln? So Lincoln opposed. There's 25 out of those total 52 that opposed that are from Lincoln. And so we have the number up here is the number that opposes and is from Lincoln. And so this equals 25 over 52. Now if you try to reduce these, you can't. 25 is only divisible by other than itself, and 1, it's only divisible by 5. 5 does not go into 52. Therefore, nothing divides evenly. No whole numbers divide evenly into those. That's reduced as much as possible. And we are done with example 3, and we're also done with the notes here. So hopefully you found that helpful. More examples in your book, 3 more, pretty similar to what we did here, but changed the numbers around a little bit there. I tried to give you slightly different situations so that you have some more helpful things to look at in your book if it's still not making sense to you. If you're one of my students, let me know in class if you had any questions. Happy to help you. Hopefully this will be very helpful. Go back, rewind, and refresh as needed. Pause, rewind, reflect, and I will see you soon.